Okay, so yeah, like I was saying, logistic regression is always used for classification settings. So we will work on a binary classifier on this data set. That is this data set. It's from this LibSVM source. So it's a large data set actually. It was around 500,000 samples. So that should give you a feel of working on real world data. And yeah, so let's start. So over here, first of all, we'll just set up this for reproducibility things. We should always seed our modules. So that's important. So that next time I'll run it, I'll get the similar results. So this is always one thing that you should start. Actually, one thing. And also share this notebook right now so that if anyone wants to run it side by side, they can do that.
Yeah, you have seeded three times, I guess. You have seeded for the torch, then random dot seed zero, and then for numpy np dot random dot. Why three times?
Yes, because each of these is for a different library, right? So it's not mandatory that all of the libraries will be using the same random numbers generators. So because of that, maybe NumPy will use a different random generator. Torch will use its own random number generator. So that's why we'll seed it separately for each of them.
And random dot seed. This is for executing in
The
Python or what?
random library. Yeah, this is for Python's random generator. Yeah, so you can take this, make a copy
No,
of it.
probably
So
no,
yes,
no.
so
Probably
like
you can
always, yes.
say team itself after the class.
Sorry, can you repeat?
I'm saying you can upload the notebook in the Teams itself. There's a section for notebooks you can upload there
Yeah,
after
yeah.
the class.
Yeah, so I uploaded this right now if in case anyone's running. Yeah, I'll also upload that in the folder. So let me get started with it. So, yep. So over here, I'm just setting a couple of my parameters. So learning rate, train size is 80. So it means that I'll be using 80% of the data set. Now test side over here is zero point 0.5. Don't confuse. Actually, this will be zero point 0.5 of the 20% of the train. So basically, we will be splitting the data set into three sets: train, test, and validation. So 80, 10, 10. That's the ratio. So let me first quickly get the data. So before we even do something, we should have a look at how the dataset file looks like. And over here we see that, okay, so this one, that is the label. These one and two, these are the labels. And actually this one colon, this means that for the feature index one, this is the value. So it's in a quite a different format. This is called an SVM Lite format. So fortunately, we have a library for that. So we can use that to get our data points. So X, that would mean that the feature vector, and Y, that would be the target labels. And I also said that we have these ones and twos. So for a binary regression, we are going to convert that one and two into zero and one. So over here, if you see that those values which are one, that is being mapped to zero, and those values that are two, that is going to be mapped to one. We should also know something whether the data set is balanced or imbalanced. So this is important because suppose our data set is imbalanced, then ideally we would like to train our data set on a in a balanced manner. So that means that the distribution of classes should be close to each other. So over here we have two classes and we can see that 51 and 48. So yeah, roughly 50-50 percentage. That's good. That means we have classes, sufficient examples for both of the classes. And over here right now we are just going to do some typecasting and converting this into matrices. So I'm not going to run this cell. So basically this is an experiment. Like sometimes our data set sizes are too large. So we would want to run it on a smaller data set. So over here, this is I'm sampling randomly 100,000 points from the data set. So like I said, the full data set size is around 5,80,000. So this is a smaller data set, but I'm not going to run it. So you can run it if your
You're
machines
talking
are.
about it's not
Yes.
dense. Why? X
Okay,
is
yeah,
X.
yeah, so
Yeah.
this
So
is basically going to be a sparse matrix. This, because if you see over here, not all of the values are given. See, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. But yeah, let me show you the tail. So basically, this is a 54. There are 54 features in this, and not all of those features are going to be there. Okay, so because of that, it's going to be a sparse matrix. So sparse matrix means only the ones that are heads, that are zeros, that are non-zero will be kept. So obviously we cannot use sparse matrices over here. So we will first convert that to a proper matrix using the two dense. So are you aware of sparse matrices?
no, if you can a little elaborate more.
Okay. So yeah, check for this example. So for this last line, we have features till 11, right? But then the next feature is 43, the number. So for features from 12 to 42, those features are all zero. Okay. So instead of writing that zero so many times, then our file will become large, right? So we can skip them. I can just say that, okay, 11, 1, and then from 12 to 43, 12 to 42, those feature values are going to be 0. So obviously, if I load it like this matrix is going to be, this is not a matrix, right? Is this a matrix? You can see there's gaps in between, right? So
No.
that's a sparse notation, which means we
Okay.
don't represent the zeros. And to dense would mean that obviously it would create a proper matrix. That means from the values that are zeros will actually become zero.
Okay. So basically, it's a redundant information which you are properly expanding into a matrix. Okay.
Yes. So where was I? Okay, yeah. So we'll be using this train test split. It's a thing. So let me show you some examples of it. So X valid and Y valid. So you can see that this is going to be the matrix and corresponding target labels. So right now, yes. So we'll come to the three steps. Let me discuss three steps or anything in PyTorch thing. The first is that data set. So basically, we have to build a PyTorch data set. So most of the common data sets that you will see in other tutorials and places are common ones like MNIST and all. And they often skip this step because the data sets are in good PyTorch format. But when you will start building things, you'll come across data that's maybe not in already packaged as libraries. So you should also know how to build up those PyTorch data sets. So first of all is the class that we are concerning is this dataset class, and it must extend the Cove dataset. So this must extend this dataset class, and it must do three functions. So init, initialization, len should return the number of samples that is there in the dataset, and get item is that if I give it an index, so it's going to return the sample at that index. So first we are going to build up this dataset class.
So we are inheriting this dataset class into this new class Cove dataset.
Yes, yes. So one of the reason for using PyTorch datasets is that obviously if you use a standard API, then you can call other PyTorch classes from there, and that's going to help later because we are going to build data loaders also. So let me just show you the sizes of these. So we have three: train, test, and valid. So obviously these are the matrices that we got earlier, right? So now I have wrapped that matrix into a data set. And the function that I implemented earlier, this get item, I can use that to get the dataset samples. Suppose a 0, 8 sample and 1. So these would be the
You could
samples at the 0.
little bit slowly covering every rows properly, then it would be clear more and more clear.
Okay, okay. So yeah. So this 0 and 1
So
over here.
we the
Yeah.
description of
So
the class, please make it clear first.
which class are you talking about?
COV dataset. What we're doing inside?
Yeah, so in the COP dataset, we are wrapping up our matrices into datasets, which are in PyTorch format. So because of that, it's going to become easier for us later on. And okay, so over here, these two functions that we implemented, len and get item. So see, now I can call len on this dataset, and it will give me the sizes of it. And I can also index this dataset by position. That is because of this function that I implemented. And the next thing is a data loader. So basically, we are not going to run full entirety of our data through the model in one go. So we'll be loading that in batches. And we will also be doing shuffling, so randomly selecting points from our batches. So for that, we need a data loader. So that is the second class that's going to be used. So we are going to create different data loaders for the training, valid, and testing data. And the batch size, like I said, I defined it earlier. So that is 2048. And so one thing that is also important is we'll pass the separate data sets to these data loaders. And also for training, we would want to keep shuffle to be true. And for valid and test, we would want to keep them false. Because actually this is going to help us reduce overfitting a bit. And so if we see what is this data loader, this data loader is basically an iterable, right? So that means it's like a list. So we can iterate through the elements of the list. So right now, actually I should show you with. So if I set up a batch size of say 2, and then if I
So data loader. Data loader is an iterable list.
yes, yes. So right now, if I set up a batch size of 2, then every time I'm going to get call give me one batch, it's going to give me two values from it, two values from the data set. If I call it 4, then it will give us 4. So batch size means the number of things that I'm sampling at together. So let me just reset that also. And over here we can see, so over here, uh, features batch. So what's going to be the shape of our batch? So remember the previously the batch size was 2. So there was going to be 2 records and 54 features. And similarly for the labels, it's going to be 2 records and 1 each. So 2 cross 1. Now, I think we've discussed about the data set. So we extended the basically PyTorch dataset class, and we built our data loaders. So next we are going to build up the model. So that is the step 2. So this is, you will see this signature everywhere that any PyTorch model has to inherit the nn.module class. And the first thing it has to do is call the constructor to its base class. And over here, we are going to call up a linear layer. So basically, so yeah, so for logistic regression, what is our structure of our network? I think logistic regression has been covered in last classes, right? So can someone
Linear regression has been
tell me
covered.
what is the structure for log? Yeah, so it's just like linear regression, but what's we just do one different thing on top of it.
We're going to have a sigmoid function in there.
Yes, yes. So we are going to add the sigmoid function on top of that linear regression layer, on top of the linear head. So input dim and output dim. So input dim is the size of our input feature, and output is where it's going to go. So as you can see from below, we have 54 features, so 54 weights, and output is that we will have only one output. So okay. So also this forward function, what is this forward function doing is basically when I'm going to call pass my data set into this data batch into the model, this function is going to get called. So we have created our model, and next thing is we are going to set up two things. So criterion, that is the loss function, and the optimizer. So we are going to use binary cross entropy loss for this. One of the reasons is for classification problems, we do not use MSE losses. Uh, does anyone know why we don't use MSE loss for classification problems? So classification problems are discrete values, right? The output of it has to belong to classes. So that means it's a discrete variables, discrete values. So for that we use cross entropy loss. And since this is a binary, so we are only using binary cross entropy. So also we will be using a standard optimizer. So optimizer is going to take criterion I just described. The optimizer is going to take care of calculating gradients and then updating my parameters. And we'll also see that what is the number of batches in an epoch. So let's clear some terminologies. So one epoch is
Sir,
one full pass through the data. Yes,
hello. Sir, binary
yes,
cross entropy loss is always used only for probability distributions when output is a probability distribution and input is also a probability distribution.
yes.
Okay.
So yeah, so if it is a classification problem, it is modeled as a distribution. So basically, in higher classification problems, instead of two, you will have the output of the model. If it's not a probability, it will be passed through a softmax function to create a probability distribution, and then that probability distribution will be compared against the true distribution. That means one and zeros. So that part will be later. Like once you do it in an image classification, where over here, we are just classifying it's whether it is, I think, COVID or not COVID. But in image classification, you'll be doing it more in MNIST, I guess. So over there, we'll be using cross entropy losses. So, okay, so like I was coming back. So what is an epoch? An epoch is like an epoch is the amount of time in which the model sees the full of the data. And the one batch is just the amount of data that the data loader gives it in one iteration. So right now, if we want to then find out what is going to be the number of batches in an epoch, we can do this, right? So 227. So suppose I change the batch size, then this is going to change. So we'll discuss about the effect of batch size on training a bit later. So I think right now to summarize, we have discussed about our model, data set and model, right? So let's go to our training loop. So the training loop is the majority part of your time and code. Like you will be spending 70 to 80% of your time here. And so right now we are running this loop actually. So we'll discuss later that even these loops are now getting wrapped up in libraries. So it's becoming faster. So first is I'm going to define this num epochs. So let me run it for small epochs actually. Yeah. So we'll be storing our losses in these arrays, and we're going to go through that many epochs. So right now we are just going to always run through that many epochs. And so over here, we are going to see that I input labels. So what is this doing is like, it's going to take one batch from it, right? And what it will do is that first of all, we are going to set all of our gradients to 0. Then we'll get our outputs from the model. And from the outputs that we have, we are going to compare that with the labels that we have received from this batch to get our loss, right? This part is our forward pass. So once we have our loss, we can just update the gradients using loss.backward. And then one thing is that, so these losses, basically, these are part of the loss of the batch, right? So if we need to track the loss of the epoch also, so we need to also maintain something called a running loss. So we'll just maintain a loss. So running loss is going to maintain the loss of the epoch, whereas this loss is the loss of the batch. So going to iteration train losses. So this is basically an array for the losses of the batches. And then we're going to optimize that step. So that's going to update the parameters. And then we can increase our iteration counts and also do something conditional over here. And at the end of the epoch, we are going to use that running loss by len of the trained data loader. So what will this do is that it will compute an epoch loss, right? So we will be storing the epoch loss in this array as well. So also we are going to be using validation after each epoch. So we'll start with the running loss valid 0. And we'll be not, since in evaluation mode we don't use any gradient calculations, right? So we are going to set torch.noGrad. So this is better for this is actually better for
Why did you
memory efficient. Yes.
now iteration mod 5000 equal to 0 equal to
Yeah, so this part
yeah
is
this
that if you want to say, I have kept it because, so suppose if you want to do, if you want to record something every 500 iterations, every 5000 iterations. So I've kept it like that. I've not done anything over here, really. But I want to show that the use of this iteration variable is, suppose I want to log something every 500 steps, then I
okay.
can use it over here. So that's why I've not done anything over here. Uh, Yeah, coming back, so torch.noGrad, that is going to disable all the computation graphs and gradient calculations because we don't need that. So we are just evaluating it. So we already have the weights. We don't need to update the weight. So, but we will still calculate the loss because we need the validation loss, and we are going to maintain append the losses. So iteration valid loss is going to be the loss of the batch, individual batch. And at the end, epoch loss is valid. That is going to have the loss of the entire epoch. So for that, we are maintaining this running loss. And so let me just run this. So see how much time should it take. So over here, I've run it for 100 epochs. So let's see, I'll run it for short.
So in every epoch I'm iterating 5000 times to the dataset.
No, 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 not 5,000, 227, 227. No, okay, okay. I'm iterating through the dataset once in one epoch. Epoch means one iteration through the dataset. Now, remember, we are selecting data from the dataset in batches. So 227 times is I'm going to go through it. So this 5,000, don't get confused to it. If I decrease batch size to say 64, right? Then the iteration count will increase, right? So don't get confused by this part actually. So our training is complete, and now we see that we have our these losses. So also we can see that it starts from 0.6 and it is decreasing. So that's somehow a good thing that we should see. And we can now, the values that we stored in these arrays, now we can use that to plot our graphs. So yeah, so we have seen this graph multiple times. Training losses decreasing, validation losses are decreasing. But yes, there's also some catches to it. I'll describe later. And also we can calculate our accuracy. So accuracy calculation I'll explain once. So because this is going to be used later. So basically we are going to again put that model into our evaluation mode with torch.noGrad. We are going to get the inputs and the labels, get our predictions. Now, this thing is that in logistic regression, if you remember, the output is a probability, right? So it's between 0 and 1. So if it is greater than 0.5, then we assign it to target class 1. And if it is less than 0.5, we assign it to target class 0. So by doing the ypred.round, what will happen is it's going to create the probabilities into classes. And then we can check the number of correct samples in a batch by comparing these two vectors, the ypred class and the labels, and then doing a sum of it. And then we can get an accuracy on it. And we see that we are getting an accuracy of 74%. So, which is setting up our good, which is setting up like this is a baseline. So, we are going to improve this. So, till this part, is everything clear with the train loop? Because the train loop is going to repeat multiple times. So, the general thing is that we have a training step, and after some training step, we do a validation step. That's it. And once we are done with the validation step, at the end, we use the test dataset only once. So that is the reason. Actually, we don't want to train our model on the test dataset, right? That is why we're using a separate data split that is called a validation. So next, talk about moving our models to the GPU. So really, this part is that we need to do two things. First is we need to move our model to the GPU and also the data that has to be in the GPU. So I think I have a GPU. Yeah, okay. So first is we'll create this device that if a GPU is available, it will use that. Otherwise, it will only use CPU. And then we are going to let's recreate the model again. We are also going to move it to the device. And yeah, how to check if a model is on the device? We can just use this. So it should return true. Okay. So we come to the training loop again. So over here, there's only literally two difference. One is that once we get the inputs and the labels, these are not on the GPU, right? So we have to actually move them to the GPU. That's it. And yeah, so there are just two steps. One is you move it to the move the model to the GPU, and for each of the data that is there, we move the inputs and the labels to the GPU. So can someone tell me what if we move the entire data into the GPU at once and instead of doing it for each of these batches? What's going to happen then?
Acha, if we move all the batches to the GPU at a time, then is it possible to run all the batches simultaneously together?
Yeah, if we move all of the batches to it, then we would have to sync the gradients, right? If we move it all of them to the GPU, then there are two considerations. First is like, first of all, our GPU memory could be exhausted, moving an entire data set. So that is why we move small batches to it. And even if we move all of the data to the GPU has fixed number of compute units. So it may be that for calculating one batch only, the GPU compute utilization is 80%. So for two batches, we can't do it simultaneously. And even if we could simultaneously run them, then yes. So what would be the order of the gradients? In which order would you apply the updates? So yes, it is done sometimes in DDP distributed data. So where they use multiple GPUs for faster training. But yeah, that is a separate thing. It can be done. So people are doing it. People train one model in suppose 8 machines and 8 GPUs. So it is done. It can be done. And yeah, so this is just that part. So I'm not going to run this again. So basically, I've run it over for 100 epochs. But yeah, if you run it, you will get the same thing. So let me come over here and have a look at this graph. So over here, we see these two losses, right? And one thing that I want to show is that previously, if I trained it for 100, so if I train it for 10, it's only going to be a bit shorter. But one thing that's very striking is how smooth this is, right? So if I decrease the batch size, right? So here's another trick question. No, not trick, like I want this session to be interactive. So what's going to happen if I decrease the batch size? What's going to happen to these curves? And I trained for only 10 epochs, right? So previously I have trained this model for 10 epochs, right? So what's going to happen to this curve if I decrease the batch size? You can guess, like, what is the difference between the gradient descent and stochastic gradient descent? So, okay,
Probably the
okay. So,
curves will move.
yes, what you were saying?
If you decrease the batch size, the curves will move apart.
Move apart. Meaning this will go up, that will
I
come
mean,
down.
that probably the difference between the train loss and validation loss will increase.
Okay, good, good. What's going to happen to the smoothness? So, is the curve going to be that smooth if I increase the batch size? So, let's find out. So, one of the reason is that one of the ways to learn this is that you change things, right? You change the learning rate, you change the batch size, and before you run the experiment, you have an indication, right? You have an indication that what is going to happen, like a guess. You make a guess, and then you check if the guess is correct. If the guess is correct, then you will learn something. But if the guess is not, still not, you'll still learn something. So if I right now, if you remember this graph I drew with a batch size of 2048. So that's a large batch size. Now I'm going to decrease the batch size to 64 and then still going to learn. Let's going to check what's happened. So this should fortunately be complete in small time, I guess. Wait, let me check. Have I changed the, oh, okay, wait. I'm going to run it for 10 epochs only. So here is the moment of truth. Let's see. Yeah, okay, 1 minute, 1 minute. Let me, I have a call. Wait. Okay, so no change, right? Actually, no change. I made a mistake. Realize this. So can someone tell me where is that mistake? If you are
You've
following the
run
code.
from only 10.
Yeah, but I ran this also for only 10 epochs, right? So basically, I forgot to reset the. See, I changed the batch size over here, but I forgot to reset the loaders, data loaders. This. So now these data loaders will have an updated. So if you see from 227, the number of iterations will also increase. See? So 7263. So if in case you're wondering, that 5000 was because of this. Initially, there were too many batches. So now let's run it once more. And I hope to show what I've been trying to show. So while we are waiting for it, can someone like tell me the difference between the gradient descent and stochastic gradient descent? These have been covered in class.
Yeah, gradient descent we were considering the entire data, and stochastic data. SGD were considering batch of data.
Good. Okay. So what is the going to be the effect of that? On the paths, see, basically in training, we try to find the paths to the minima, right, of the convex function. So what is the effect of using a
In SGD,
stochastic?
it is
Yes,
In SGD,
yeah,
the curve will be a bit edgy while coming downward.
yeah.
yes. That is that is the answer I was looking for. So SGD, the path will be very noisy because we are using only an estimate of the actual data set. So the curve will be a lot sharper and not smooth. It will definitely not be smooth, and there will be too much edges. So, and that is, I hope, is going to come. So you can see now this edges. So compare this curve with the curve for this, right? So clearly batch size 2048 is better, right? So it would appear so, yes. But okay, let's see. So we can also calculate the accuracy. So right now we are now going to discuss two things that are going to improve our performance further. And so, okay. So can someone tell me which of these two models is possibly overfitting? This one and this one.
Second one, of course.
Okay, okay. Yeah, so the reason I'm putting so much emphasis on these graphs is like that's during training really when you're trying to find it, you have to look at these graphs a lot, and that's going to tell us whether we should even continue training or not. So, okay, discussing about improving performance, first is LR scheduling. So, LR scheduling is very simple, is that during training itself, we try to change the learning rates. So, over here, all of this training is done using one simple learning rate. Okay, so by the way, has Adam been discussed in today's class? Adam Optimizer?
What? No, no, it
Is
was
Adam
not discussed.
Optimizer been discussed in today's class?
No.
Okay, okay,
Not today.
okay, okay. So in learning rate, basically learning rate scheduling, we are going to change the learning rate as we do the training. So that thing that does it is called a scheduler. And really, the code for scheduling is very simple. So if you remember this train step and then the validate step, and after that we just call the scheduler dot step. So I hope these two function parts are very clear. So this was the training part, and this is the validation, and this is just the number of epochs. So let's run it. So I'll also see that there are many types of scheduling algorithms. Okay, and let me see. I think I have given it here. Okay, so there are many scheduling algorithms, and you should know which one to use. So by the way, this is the official documentation for PyTorch. So let me just add it here also, in case next time you can see.
I'm initializing scheduler with three dots. What? I didn't get that.
So these are okay. So this part is a bit of coding jargon. Basically, we want to shorten our code. Right. We want to. This is not a code, by the way. This is actually just a screenshot. So basically, this shows you the algorithm in a short way. So see, training loop. I'm not showing the entire training loop. I'm just showing something dot dot dot. That means it is going to train. So this is not the code. So if we come over here, we see that there are many different types of learning rate algorithms. And one learning rate algorithm that I'm going to use is the reduce LR on plateau. So basically, what this means is that once the metric that we are tracking that does not improve much, we are going to decrease our learning rate. So we are going to decrease our learning rate and then try it. So basically, uh, yeah, suppose I'm tracking validation loss, right? So if my validation loss is decreasing good, I am good. My learning rate I can keep maintaining. But let's say my validation loss has started decreasing less. Now, by the way, if you remember in convex functions, when you reach towards the minima, it starts plateauing, right? It starts going into a very long curve. So that means I over there I need to use smaller learning rates. So because of that, reduce LR on plateau is something like that. So it's actually going to do that. Basically, it's going to track one parameter, and if it's not going to improve, it's going to decrease it. So yeah, so right now I am again initializing the model, and over here I'm going to call the optimizer that I defined min, and patience equal to 5. Patience over here means that patience equal to 5 means that for 5 epochs if the performance is not improved. By the way, there are many of these parameters over here that are actually default, so I'm not giving you much. I'm not writing them again. So factor of 0.1 means that every time my scheduling is going to happen, my learning rate will decrease by a factor of 10. So initially it was 0.1, then 0.01, so like that. Okay. I've talked about the scheduling. So let me also talk about early stopping. Uh, yes, so can someone explain to me what is early stopping? And then I'll show the code. You will understand it very easily.
If the train and validation losses are moving far apart, then we stop it early so that we do not move worse.
Okay.
In terms of
Okay.
reliability.
So that's 70% correct probably. But yeah, we don't focus really on training losses. We focus on validation losses. So basically, if in the validation loss, so over here, see, if the validation loss is
The
not
difference between train,
improving, okay, yes,
yeah, I just said that. I mean, the gap between these two is increasing. It's better to stop early.
okay.
If I
Yes, yes, that is
if I'm
true. See, training
increasing the
will
number of
always go down. Training loss will always decrease because for training. And then the way to implement it, the way to implement it is that if we look at only the validation way, and if the validation loss is increasing over the patient's epochs, that means we have a patience of say 10 epochs. Then we say that for the last 10 epochs, my validation loss is continuously increasing. That's why I'm saying it is, we're focusing on only one loss because training loss is always going to go down. So if my validation loss is constantly improving over, say, the last P epochs, so then I can detect it. So early stopping it. So let me show you the code over here. So yeah, so here is it. So basically we are going to start with stop training equal to false, and we are going to only do the early stopping once the number of loss, once our epoch number is greater than patients, right? So this is what's going to do with that. So once that is true, we are going to set stop training to be true. And see, this part is we are going to iterate through the last patients. So patients I have set over here to as 10. Okay. So good value of patients is 10. So for the last 10 values, I'm going to check the loss. And if my loss is less than any one of them, right? So this is one way of how I have implemented it. If my loss is less than any one of the losses in the last 10 epochs, that means I should continue training and I will set stop training to false. But if it isn't, then stop training will be true, and that means I should really stop it. And yeah, so that's what's going to happen over here. And also for the scheduling step, so scheduler dot step epoch loss is valid -1. So epoch loss is valid, if you can understand, is that over here, then I'm storing the epoch loss, epoch validation loss, right? So I'm storing it in this array. So when I'm going to step on the scheduler, I'm going to give this loss value. So let's run it. So actually, this is going to take time. So I think
you
how much I have run.
get it.
Yes. Yes.
The
Hello. Yes. Can you repeat your question? Sorry.
I was just asking if you can repeat this part again.
Okay. So for basically early stopping means that if my loss is less than any one of the last, say 10, so my patience is 10. So if my loss, current loss, is less than last 10 losses, any of the last 10 losses, that means my validation loss has, then there's still scope of training. But if my loss is not less than any one of them, that means my loss is continuously increasing for the last 10 epochs, then I can stop training. So there are multiple ways of doing this. So you can also say calculate the average for the last 10 and then compare that average with the current one. But yeah, this is the more easier way to understand it. So the stop
In
training,
the
so in,
scheduler,
yes,
in the
scheduler.
scheduler, the step, yeah. What does it?
So,
Epoch underscore losses minus one. What does it mean?
so -1, that means this is Python notation. So -1 means the last loss in this array, right? So
Okay,
the last
last.
loss is going to be the loss of the last epoch. So on the last epoch, I'm going to step. So, okay, so 467. Okay, too much time. Okay, I cannot run it now. But okay, so if you look at the outputs, so over here, I'm plotting the training loss, validation loss, learning rate, and the validation accuracy. So you see that the losses are decreasing, but what I want to show is, okay, look at this row for epoch 21. You see that my validation loss has become not much improvement, right? 500, 0.518. So over there, my scheduling is kicking in and my learning rate is actually decreasing. So it also decreases, see again further, it is decreasing by a factor of 10. So it's decreasing from epoch 21. And then it again decreases on epoch 31. So you see, this is how basically, even though my losses are not, see, if I look at the number at at 2 or 3 decimal places, I see 0.518, right? So I can say, okay, my loss is 0.518. But what I'm really saying is I want to go as close as possible to the minimum. That means to last level is really flat. So 0.518. So because of that flat level, towards the end, you see, look at our learning rate. So our learning rate has decreased so much, but our loss is decreasing. So that is why we are actually decreasing the loss when we move towards the minimum. So is that part clear why we are actually decreasing the learning rate?
Yeah.
Okay. And we also see that for the last 10 epochs, so 0.518, see, the last values of the epochs are same, the last loss value. So 0.518,105. So because of that, our patience parameter is kicking in and we are stopping the trading at epoch 58. So let me show the graph. So yeah, so this is what I was saying of the learning rate. See, the last part from after epoch 20, our loss is not at all decreasing much, right? But we are still training because over here we are not see, but our learning rates. So actually, yeah, the green part is the learning rate. Okay. The blue part is the training loss and the red part is the validation. So initially it's quickly moving down, right? And yeah, so initially it's moving a lot, but towards the end, it's not moving much because we are also see decreasing. Initially it was 0.25. We decreased that. We are also again decreasing it. And towards the end, it is really small. So towards the end, it's really small. So with small learning rate, it's not going to change much anyway. And then we say that our training is complete. So, these two things that we used to improve our performance. So one is that we are scheduling the learning rate, and then the other is that early stopping. And if we see that we can get the accuracy also 75.69. So it's slightly better than previous. But one thing is that this logistic regression thing that all we are doing is we are getting accuracies of near about 75%, right? So I think I've described it below. So what is one way of understanding why this is happening? So let's start like the size of our data sets. If anyone remembers, what is the size of it? Around give an estimate. What is the size of our data set? Okay. So the size of our data set is around 500,000, 500K. And how many parameters is there in the logistic regression model? So we have 54 features, right? So how many parameters are going to be there in the logistic regression model? So I'm trying to keep this class interactive. So if we have 54 features, then how many parameters are going to be there in the logistic regression model? You can give an
55.
estimate also, not exact answer.
54.
Yeah, correct. You forgot one for the bias, but yeah, 55. So with 55 parameters, we're trying to learn a 500,000 data set, right? So that is one of the reasons why, despite so much training, we trained it for 60 epochs, we are still getting what, 75% accuracy. So we are going to try to a deeper model. So since this is a deep learning course, we'll also talk about deep models, right? So yeah, so also this is one thing that you can run. So this count is going to actually give you the number of trainable parameters in any model. So okay, so let's define our model. Is that first is it's even though it's not really very deep, but it's deeper than the previous one. So we have an hidden layer. So one input layer, then a hidden layer, and then the output layer. So this is like the simplest deep neural network. So from the input DIM, that is 54, I'm going to map it to hidden size. And after the hidden size, as you can see, I'm going to put up an activation function. So the activation function I'm using is leaky ReLU. And yeah, so also you can see that I have tried different activation functions, and that is why I commented them out. So when you're running the code, you can just comment this part and then uncomment this. It's going to work. But yeah, so you can try out different activation functions and tell me which one is giving you better results. But I'm using it linear ReLU. So from the hidden output, then we are going to pass it to the activation function. And after the activation function, we are going to give it an output. And once we have an output over here, we are going to, in the forward pass, so self.model x. So this is one cool way, is that I can put it in a nn.sequential. So basically the model will flow like this: input to hidden, then ReLU, then hidden to output. So this is one short way of writing it. And we have put up a sigmoid function at the end of it. At the end. So this is like a deep logistic regression. I'm not sure I can call it that. But yeah, so think of it like a deep model, but on top of it, we still have a logistic regression head. And okay, so I'm not going to repeat all of those. So you can see I've kept most of the part over here. One thing that I want to show is that previously, I think we came to this conclusion that for batch size 64, this curve was not very good, right?
I think you were describing the how will the values be calculated in the pass rather than being deep model. In that and the yes.
Yeah. So nn.sequential, basically nn.sequential means I can
Yes.
see. This is what previously what did I did? I put it through nn.linear and then I put it to sigmoid, right? But if you have multiple linear
Yeah.
layers combining one after the other, so instead of calling each one, I can wrap it in an nn.sequential. So it's going to be a sequential model, and then that together is going to flow through it. That's it. So see self.model x. That means x comes, it goes to the x's input dimension, gets mapped to hidden dimension, then ReLU, then hidden, then output. And then once I have the x, I can call out sigmoid on it. Basically, I can write it separately like this also, linear. See, what I mean to say is, this is a shortcut. I can write it like this. I can say x equal to linear x equal to ReLU x equal to linear x, right? I'm not writing exact code, I'm just showing this, right? So instead of that, I can just wrap all of this in one single model and call that.
Okay.
Okay.
Yeah.
So right now I have, yeah, so, okay. So I have done a hyperparameter search on a good set of parameters for this. But yeah, coming to it. So previously, I think in this graph, when we were talking about this graph, right? So what is the size of this graph? Batch size for this graph? If anyone remembers?
You set it to 2048 or 64.
Yeah, this one is for 2048. So it's very, see, you can guess also. 2048 is going to be really smooth. And
Yeah.
64, it's not smooth. There are curved edges on that. So previously, I think we thought like this was not a good batch size, right? But yeah, so there's also learning rate and a lot. So one hyperparameter that I have found that is giving me good results is this. That means that the batch size is 64 and the learning rate is 0.5. So once you have this notebook, actually, I want you guys to keep trying hyperparameters, see if you can get something better. So yeah, so input dim, so 54. So from 54 features, I'm going to map it to 108 features. So think of the hidden dim as like I have 54 features. I'm trying to learn 108 features from it. So think of it like that. So because I want it, I want more learning, right? So actually, one experiment you guys can do is instead of 108, try 27 and see what happens. Right, half the number of features. Try and let me know like if your performance is still improving.
Number of features, did we duplicate it or sort of produce a linear combination of those and produce new? How did we increase the number of features?
See, what is this hidden layer, by the way? This is just a number equation, right? So what is the one parameter for H1? H1 is W11 X1 all the way up to W1 X54, right? So H108 also I can just add one more equation to it, right? It's a set of equations. Think of it like that. No. What is a linear mapping? A linear mapping is a multiplication of a matrix on a vector, right? So in the matrix, I can add any number of rows, right? As long as I ensure that the multiplication is possible.
The input size would be of 54 plus 1. Column vector x1, x2 up to x54. And I'll feed this input to the model. Now, how come I increase this input size to 108?
So this is our transformation, right? So what is x? X is 54
It's a 54 by
So x is a row vector. Let's say that x is a row vector.
it's transpose.
Yeah, let's make it better. Let's make it a column. Yeah. So now, as long as I have to multiply x, I can put anything over here. Right? I can multiply this, right? These two vector matrices. I can put anything over here. That's what 108 over here will actually become. So basically, you can think of it like adding equations, more equations to the solution. So this is a linear mapping. And we do this all the time in CNNs. When you're going to come to CNN, you are going to see that we are increasing the features in one layer.
No, I'm
Yes.
saying you have changed x finally to 108 cross 1. Because this is AX, it's a metric that gives with x.
So you can multiply these two matrices, right?
From 54 plus 4. Yeah, we can multiply. Yeah.
Okay, so so basically, see, you will be doing this in convolutional networks and many times. In one layer, you will be increasing the hidden size. In another layer, you will be decreasing it. So it is not like, think of it like if my data like
features are of course independent variables which describe the data. So producing new features.
We are not producing new features. Okay.
As good as
Okay.
coming up with.
We are not producing new features. See, the correct way is we are not producing new features. We are producing a larger. We are producing a more detailed, I would say, representation of it. The exact correct way is that we are not producing more features. The features is always 54, but we are producing a more detailed representation of it. So that is called representation learning. So hidden layers are actually learning better representations of it. Suppose I can say that for first 54 features, I can track something of the feature, and for another 54 units, I will track some other part of the feature, right? So that's what it's really doing. It's just learning a better representation. So actually, why don't you try it? Reduce this to 27, okay? Reduce this to 27 or 30 or something like this, 54, and check if the model performance is better. I'm also curious to learn. So if you can do that and let me know, it's going to be good. So yeah, so coming back, I think we are overshooting time. So we have 64 batch size, learning rate is 0.5. And yeah, so if we print the parameters, okay, I think I not defined this. So number of parameters is clearly going to be increasing. See, over here we have 6049. So compared to 55 parameters previously, it is better. So we expect this model to have better performance, and it does also. So okay, training loop is almost same. Actually, you could run the previous training loop itself, but I wanted to keep the output separate, so I've just copied that. So there is nothing, no change, early stopping, stepping, and all. So if you can see, I have run it for how many? I've run it for 70 epochs. And in 70th epoch, it has stopped. And look at the learning rate scheduling. The learning rate scheduling has again come into place. So see, initially it started with 0.5, right? And then it has become 0.05. And then again, it has become 0.0005. So the scheduling is working out. So scheduling is, and see, look at our accuracies. These are much better anyway. So if we plot it again, you'll see this. So we see that. So actually, this spike part that we know, because this is going to be a small batch, right? 64. So it's going to be a lot of spikes. The spikes are still here actually also. The spikes are here also, but it's just that the learning rate has decreased, right? So because of the decreasing learning rate, the spike multiplied by that learning rate is also decreasing. That is why towards the end, it may appear that the curve is smooth, but if you zoom in over here, you will see still those spikes. And yeah, so training loss is always decreasing. And once we compute the accuracy, we have 86.83%. So compare this with our logistic regression model. What was the accuracy around? If anyone remembers?
It was about 70 something percent.
Yeah, yeah. So from
74.
it was 75%. Yeah. So from 75% on the pure normal logistic regression, we have come to 86% on the deep regression. And I want to see if this can be better. So those parts are exercises for you, right? So yeah. So one thing what I want you guys to do is try with a really small learning rate. Okay, 0.05. So in 0.05, you'll probably see overfitting never occur, but you should try it. You can also run it on, say, a smaller data set. So if I decrease the number of data set size, what is going to happen to this curve? Like, if you not think of it in terms of the y-axis, the x-axis is going to contradict if you think about it in iteration, because the overfitting will start sooner, right? So this is one thing that you need to understand. The number of parameters in a model and the number of records in a data set, right? So if we have huge number of, if the size of data is huge, a large model will be need to overfit it, right? But if it is a very small data set, even a small model will start overfitting. So that's why I'm asking you to run these experiments. Say from 500,000, you just take 100,000 and see when does it start overfitting. Okay. So also experiments is okay. So that is your, these are experiments. Exercises. So again, these are all for your sake. The only way to learn actually deep learning, actually from the way of a practicing point, is that you can learn a lot of theory about it, but uh, you should be able to apply that theory in practice. And people are going to say, come up and ask you like, okay, if I decrease this, then what is going to happen? So some intuition you should have. Because of that, I want you to try out these things. Okay, so okay. Also, the early stopping functionality, if you check, it can be improved, right? So over here, see, when we are stopping the training, we are always selecting the model weight for the last epoch, right? But that is not the best. Where is this? See. the current early stopping code that we have, we are stopping this over here, right? But when we stop it over here, this is not the best model, right? Which is the best model? This part. So we
I
have,
I mean,
you want me to repeat this
which
part?
part of the code is reflecting that? No. I just have a question here. Which part of the code is actually reflecting this fact, the number of layers?
Layers? Layers
Number
or
of
epoch
layers in this,
in the
they are
model?
interchangeable. See, yeah,
In the
numbers.
model. Yeah, I didn't get you. Can you repeat? Are you talking about layers or epochs
When you
or
have a
what?
neural network, no, I'm talking about layers. Like every layer has nodes. Like we seen a picture. Every layer has nodes.
Yeah,
So
so the
layer one, layer two, layer three.
model definition, right? Where we are defining the model. See over here, the layers, one layer, this is another layer, this is the activation function, right? So
This is
layer
what
one,
characterizes the node. I mean, how the value will flow across the node. So there are one thing is number of nodes in the model, and the other thing is layers.
yeah. So nodes are, see, when you think about nodes, those there are actually never nodes, right? Those are values. And those values are
Yeah,
stored, computed, the gradients are calculated, and those values are given away. The only thing that is stored in a layer are weights. So you can always check a layer, weights for a layer, right? You can always check the weights for a layer. Model dot team.
no, I'm just saying how are we characterizing a node and how are we characterizing a layer in terms of code?
So nn.linear, we are using PyTorch libraries. So nn.linear is one linear layer,
Okay,
one
it's only
transformation.
okay. So in a layer we can have many number of nodes of some how we actually manipulating that. Layer one can have let's say 54 nodes. Layer two can have I can make it short and say 15 nodes. So
Yeah, so that I think we discussed, right? Over here, when we are given the size mappings, when we are defining the model itself, over here we are giving, right?
no,
Where is it?
we change the input dimension probably. I'm saying in intermediate layers I want to
Yeah,
change
so
the number
input
of
input to
nodes.
yeah, so input to hidden, right? Hidden dimension. And then hidden dimension to output
Okay,
dimension. I can change the hidden one over here. The hidden dimension is only I'm talking about 108. You can change it to
okay.
2027. Okay, so yeah, coming back, I want you guys to improve the early stopping functionality. So currently, the early stopping functionality is actually I should leave something for you guys to do, so you will also learn. So currently, the early stopping functionality that is there in this notebook is it will stop the training over here, right? And it will use this model's weight, right? But I want to use the model's weight is best this. So what we should do is we should keep saving the model weight for the last p epochs, and once we have stopped it, reload the best weight model. Okay, something about checkpointing. So you can do that. So check PyTorch how to save and load models, and that you should check. Try to do it in a efficient way. That means it's not efficient if you store everything in memory. So try to do it. That part is you have to do it because uh, actually is this part clear? Like I think most of you are not responding. So right now the
Yes,
model is
yes.
actually going to give this part, but I want to give the model at this part. So extend the code and
How will I check if this particular, let's say,
So when you are calculating the epoch only, right, you have the validation loss, right? So you can just save the weight and the validation loss. And then when you have stopped it, compare against the last saved models and check which one has the best validation loss. You can also do it on a different metric. Let's say instead of loss, you are trying to test it on accuracy, right? So you can also save the model weight and the accuracy. And then towards the last, you just select the one that has the best accuracy.
can you do it like this? That I don't know. Sometimes the runtime of the Colab, I guess, gets disconnected. So before the runtime of this, let's say model takes a much longer time to run, and I don't know when it will. It might suddenly disconnect. So the moment before it disconnects, I can save the checkpoint and uh, wait. I save the checkpoint.
Yeah.
Can you do
So
it like
about that, you can never know when Colab is disconnecting. The best you can do is connect the Colab to Google Drive and then periodically save your checkpoints to the Google Drive. That's the best you can do. Right. So that means you can say
If you
that I
could,
will save the checkpoint after every epoch. That's it. Okay. So a couple of things.
if you could show.
Yeah, it's not that different. You can search it on Google. It's not that different. Thing
Okay.
connecting Google Colab, connecting Colab. It's 2 lines of code. So you can it's not that difficult really. Basically, if you run 2 or 3 lines of code, what will happen is you will have another folder over here, and that will be your Google Drive folder. So you can just normally use like you are using these folders, right? So you can normally use those folders as well. Actually, I have it. Wait, I think I should be having it. Let me check. So since you were asking how to connect Colab to Google Drive. Yeah, I see. It's 2 or 3 lines of
Okay,
code. It's not that
just
much.
training will be saved, right? And the
Yeah, you
point when
have to
the
connect.
Colab will disconnect,
Yes, yes, yes,
till that point, my training will, okay, parameters received.
yes. Yes. So, okay. Yeah, so first is exercise. Exercise number one is you have to extend the early stopping functionality. As a second thing is that over here, this neural network has one hidden layer, right? So you can try even more deeper, right? So you can use 2 hidden layers, 3 hidden layers, 4 hidden layers. So the main thing is aim. I want you guys to aim for 90 greater than 90% accuracy, right? So best we have is 86. So try getting more than 90% accuracy, right? So, oh, also, can someone tell me which part of the code only we have to change? There's literally very little part of the code we have to change for using a different network. Do we need to change the training loop?
Which one you're saying? Early stopping?
No, no, so not okay.
Extending the early stop.
No, for extending the early stopping, we have to improve the training loop. I'm saying that if I want to use a more deeper model, that means use more layers and all. So which part of the code I have to change? I'll have to change only one part of the code.
You want to
The rest,
include more layers.
so
The
I'll only
part
have to
which you have
change this.
defined uh, deep learning related thing.
Sorry, what are you saying?
Yeah, you have defined this hidden dim input.
Yeah, so we actually have to just change this part.
So yeah,
So just use a different model, the rest, and also use those things. These parts you have to understand what is going to be hidden dip. So just change this part and then run it. Try out a different model. So I want you guys to aim for more than 90% accuracy. Actually, the reason I'm giving this dataset is I've worked on this dataset previously, and over there also previously 1 year back when I was working on it, I could never get the accuracy beyond 75 using only logistic regression. So I thought I should try it now. So yeah, so 75% logistic is there, but with a more deeper network, we got 86%. I got it. So I want you guys to aim for more than 90%. So if it is possible, then do let me know. You can ping me and tell me what network you used. So, okay, also some further tips for the learning rate scheduling I have discussed. So PyTorch Lightning. So if you see, almost always the training loop is same, right? In every part. So this training loop can be easily automated, and early stopping and all of these features that right now we are manually coding and implementing it. These things have been put into libraries. So that part that encapsulates the training loop is called a trainer. So we have good frameworks, PyTorch Lightning framework, Hugging Face trainer. So these things are going to do it much better. So they will take care of the training loop. They will do the device management. That means if I have to run it on one GPU, I can do it. If I run it on two GPU, I can just change a parameter. It's going to change on two GPUs. But right now, if I have to manually do that, if I have to actually code it, then there is scope of a lot of errors, right? So PyTorch Lightning and all of these things are going to encapsulate the training loop. So you can definitely check out this. It's a very cool thing, and you'll be able to run very fast codes in very little time. So from one GPU, you can scale it to 10 GPUs and just change one variable. Also check out TensorBoard. So actually see all of these graphs. I have to store the metrics. I have to go and plot the graphs. So there are dedicated libraries. One is called TensorBoard, and this is really good. It's going to show you. It's basically if you just in a few steps, it's going to automatically plot your graphs. It's going to monitor your training and all. And once you are done with these two, I want you to use a completely different. I want you to use these two things to use a completely different neural network on a different data set. So that's going to show you that we have learned things from it. So yes, let's wrap it. So questions. So if anyone has any questions, this is your time.
The last question is you want us to do logistic regression with some other model, which could do more better. Is it?
Yeah. Yes. So first is you try to use a deeper model and then improve the accuracy beyond 90%. And then you go and learn PyTorch Lightning and TensorBoard, and then try something else. Maybe it can be anything. Just use these two things in your model. See, basically, most of the code that you will see is going to use these two frameworks. And if you are working on now, research is everything is becoming part of a framework or library. So you will hardly ever see training loops like this. So you should have you should know the fundamentals beyond it. That is why I showed the training loop. But you should also, if you're working on this research, you should also know how to use it, how to use the quick things. That is why once you have PyTorch and TensorBoard, once you know these two things, you can probably use a different, try out an image classification dataset. So yeah, I think I gave you too much work, but what I'm saying is that you don't have to do it. It's up to you. If you do it, you will learn. And yeah, so the more you run, more you train neural networks, the more you will start to anticipate how things are going to change and do that. Right? Like this batch size, the effect of batch size. The learning rate also thing I want you guys to do. So if you basically if you go try it with a really small learning rate, you'll see it takes so long to overfit. Okay, so I think that's it. If there are any more questions, no, then yeah, we can disconnect.
Thank you, Shan.
Okay. Thanks everyone
Thank
for
you.
joining. Thanks. Bye.